Okay, we are going to talk about the electric potential. So there'll be a very important chapter. So it'll be about that the electric field that has a curl equals zero, and with that, we will have the potential that is easier for us to use because electric field is a vector field. It has three components, but potential is a scalar. So scalar is easier to deal with. So we'll do talk about it now. All right. Okay. So uh, potential. Here we first check some function like this function y uh, along the x direction. So with that, by taking a curl, this thing is not zero, but because we know earlier that curl electric field will be zero, so this vector field cannot be a valid electric field. Means no possible charge distribution can make such a field. Okay, so in general, finding a vector field satisfy electric field property is very difficult, and it is a vector problem, so it's very difficult to do it and very difficult to solve. A method will be introduced here to make finding the electric field much easier by solving a scalar problem. That is for potential anyway. So recall that there are four identical things. One is the curl of vector field equals zero is equivalent to the path integral of the field, which along certain doesn't matter which path, but as long as the initial and final position is given, the value will be identical, regardless what kind of path you have. And the third one is actually a loop integral or a closed path integral will be zero. And the last one is this vector field is equal to the gradients of a scalar function. We said the negative sign, but it doesn't really matter here. So, but we actually said it here. So these four properties are identical. So in other words, for electric field, which have the property of curl electric field equals to zero, means there's exist and potential that satisfy this electric field. So taking the negative gradient of this potential, it will equal electric field. So with that, we are trying to find the potential that we can describe the electric field. Okay, so from earlier, and we know the path integral with a closed loop of the electric field will be zero. And with that, we can use Stokes theorem to get the curl of electric field do the area of the integral will be zero. This is from Stokes theorem. So there was a path integral, okay? Because with a closed loop, there'll be zero because the value for the integration is identical without considering which path you are choosing. So that's it. So the path one and path two are equal. So with path from A to B will equal to the negative sign from B to A. So sum them up will be zero. Because of the independent of paths, the integration of electric field between 2 points can be defined as something like this. So we define the potential of these 2 points. One is the reference point, the other point of interest, which has a location R. And we define the electric potential is the integration of electric field, taking the path integral from that reference point to the point of interest. That's it. So because this path integral is a scalar, so that give us this potential is a scalar. And potential difference between these 2 points will be just simply taking arbitrary, taking the integration from the reference point to point B and point reference to the point A, and then do the sum together, so we can have it, and it'll be equal to the integration from point A to point B. That's it. That's the basic idea. Okay, so the fundamental theory of gradient theorem, fundamental theorem of calculus of line integral, it'll be something like this. Earlier we talked about things like this, and we know that taking the gradient of a scalar field is a vector, and taking the path integral will be this one. So it's essentially just taking the value of this scalar field at point B and point A and minus minus it. That will be it. So by that, this, by definition, what we define as the potential V is actually just satisfying this thing. So eventually, we can conclude that the electric field is equal to the divergence of this potential, this electric potential, and taking a negative sign. So an electric field has an associated potential V, which what we really wanted. They are equivalent. So these are the most fundamental relation of the potential, and we are going to use this potential later on. Okay, based on the fact that the curl E equals 0, we just got the conclusion that we have the potential, and the potential is essentially just the path integral of your electric field along the path. Anyway, so be aware that this potential, electric potential, is not potential energy that you learned earlier, but they are related but not the same thing. Just be aware of it. A surface with the same potential is called an equal potential. And that's kind of, yeah, very straightforward. So knowing potential, that because we have this relation. So as long as we know the potential everywhere, we know the electric field everywhere. And potential is a scalar, but electric field is a vector. So vector is hard to deal with because there are three components, ex, ey, and ez, and each can be a function of x, y, z. So it's very, there are so many elements. But potential, actually, it is a scalar function, so it has only one component, which depends on the coordinate. It's not a vector, so it's easier to deal with. And these three components are independent to each other. So, uh, so we take the curl of the electric field, we would got some relation like this one. So that's why these three components, even though it has three components, but it has a relation that been required by the curl of E. But still, it's still very complicated and not too easy to deal with, even though it has some relation. But this relation is also very hard to deal with. Anyway, so we would like to use potential to be the way we describe an electric field or just electric potential to describe the behavior of the electricity or electromagnetism issue. So potential is rather simple and easy to deal with. Assume original reference point is O, so our potential can be written at that particular point of interest R is the path integral from the point O to the point of interest. Okay, so if choosing another reference point, O prime, the potential will actually change. So that's the thing. Uh, just be aware, this point is just telling you another point. It's not about the source. Okay, it's just the origin or the reference point we choose. So the integration path O prime to R can be split into O prime to O and O to R. So the potential at that particular R with respect to the reference prime, O prime, is something like this. We can just split it and just write things like this. This is a constant and plus a potential that we had earlier. So in other words, this statement telling us choosing the reference point will give a different potential. And it's okay because earlier we said we can use the gradients to potential and get electric field. Since this is constant, the gradients of a constant is zero, so it still doesn't influence our electric field if we want to obtain it. So it's fine. So changing reference point is just adding a constant. If calculating potential difference between 2 points, it's still the same thing. It's okay. Also, note that the constant does not influence the gradient since the gradients of a constant is equal 0. So the uh, gradients of V prime using a O prime as the reference is equal to the potential. Well, as we talk about. So the electric field doesn't is okay. It's not influenced by the choice of the reference point. So the reference point for potential is just a matter of free choice. So you can choose any reference point you like. Okay, so ordinarily, infinite far points are usually said to be zero potential. So if there is no good reference point, you usually pick something easier for calculation. So infinite is probably a good one. This works okay if the charge is distributed with a finite range. In other words, if the charge is just distributed locally, so the infinite far is okay. But some problem you have the charge distributing very far, and there'll be a different thing to consider. If the charge extends to infinite, like line charge, plane surface charge, potential at infinite should not be set to zero. In reality, no charge extends to infinity. Therefore, choosing zero potential at the infinite is usually okay, usually fine. Potential obey the principle of superposition too. So just like force obey the superposition, so the total force is the sum, the vector sum of each force contribute to certain object. The force act on the test charge is the vector sum of each charge acting on the test charge. So it's fine, since the force equal to the charge times the electric field. So total electric field is actually the electric field at the test charge contribute by the first charge, second charge, and you can sum them together. So total electric field is the vector sum of the electric field. Each charge contributes to the test charge position. So since that, the potential is just simply the path integral of the electric field. So we can still have the same thing. So the potential is also satisfied the superposition principle. So by integrating electric field from a reference point O to the test charge position R, V is obtained. So the total potential is then the scalar sum of each electric field contributed potential. So it'll be total potential is potential contribute by the first charge, second charge, and so on and so forth. That's it. Okay, so now about the unit. So the force, this is something we are familiar with. Force is in unit of Newton, and mass is kilogram. Acceleration is meter divided by times square. So the force equal to here the charge times the electric field. So Newton equal to Coulomb, which is the unit of charge. Electric field is Newton per Coulomb. Okay, that's fine. So usually we will say the potential is in a unit of volt. Okay, but by definition, your fundamental unit is not including something called volt. But by definition, your electric field is actually Newton per Coulomb. Taking the integral, line integral, is a meter. So in other words, you can transfer Newton into this kilogram meter divided by second square. So into something like this. So that will be uh, another unit presentation. And we can also switch it into joule per coulomb. So that is different way to represent it. But be careful. Typically, our most fundamental unit here we use is S in SI unit. And we can have several things that you have a unit of the basic fundamental unit are meter, second, kilogram, mole, candela. This is for describing light strength, and Kelvin, temperature, amp. That's it. So here are the fundamental units. So basically, Coulomb is not a fundamental unit, but Coulomb can be related to with the current, which is in amp. So Coulomb earlier, somewhere you probably learned Coulomb equal to the current times T. So how much charge flows through in a certain time uh, mm, is the current. Okay, that's it. So here, Coulomb is not a fundamental unit. Joule is not a fundamental unit. Volt is not a fundamental unit as well. So here we are considering these are the fundamental unit, but volt usually in electromagnetism or electricity we like this unit, so we use volt as a unit for potential. And electric field, there'll be uh, another way to represent it, like electric field will be in a unit of volt per meter. That's it. You can move the dl, which has unit L, m here, meter here. So it will be volt per meter will describe electric field. That's the thing. So basically, these are the common on the unit. All right. Okay. Example 2.7 is a potential of the uniform charge spherical shell. So it means that you have a charge distributing on a sphere with radius of r. So calculate the potential of a point outside the sphere. So, well, everywhere. So finding inside and outside the shell. So outside or inside. For outside, using the Gauss law. So basically, you have the electric field and you can have the potential. So you set a point that at the infinite, the potential will be zero. So we just can take the integration from zero to the particular point r. So electric field at is, yeah, just earlier we know that when we have a charge distributed on a shell is equivalent to be considered as a charge within the center with the total charge that included. So that's relatively easy one. So the potential is just like taking the integration from the infinite far, which is zero, and to that particular point r. So we can easily calculate it. So here is the potential of the at this point of interest P, which has distance from the center of the sphere or shell with a distance r, small r. So that's it. But for inside, that uh you will have r, this small r less than capital R, which is the radius of the shell. So the potential can be considered as from the infinite to this shell, and then the shell to that particular R location inside this sphere. So that's it. So let's do it. So because inside there's no potential change, so the second term is, well, is zero. So there's no electric field with it. So potential is a constant inside the shell. So whatever inside the uh, shell, you have a constant potential. So although the field is zero, potential depends on what happened outside. So inside the potential is a constant, but and also there's no field inside it. From so now from physics we know one thing. This is what we just discussed. The curl E equals zero, but the Gauss law tells us the divergence E equal to the charge density and it's on now. So these are what we have. And now we have a definition of potential. So we just put it in. We can take a look at it. So this part is easy because this one actually directly lead to the conclusion of we can have a potential, which is scalar. So the curl of this uh, gradients v equals 0. This is always right. So we go nowhere on this track. But with the Gauss law alongside with this electric field equal to minus gradients potential, we just put it back in. We get something more interesting. Okay, here we got Laplacian. The Laplacian operator or del square of this potential. So we have on the right hand side is the charge density divided by epsilon naught and with a negative sign. This is called a Poisson equation mathematically. Just you got a Laplacian of a scalar function and with the right hand side which is not zero. This is called Poisson equation. This is a French mathematician. In French it means fish. Anyway, so if the and this is the more general form. So you have charge, you then write things down like this. But in a special case, when the zone equals zero or there's no charge distribution or source free, this is Laplacian square scalar function equals zero. Mathematically, it's called Laplace equation. Okay, this is looks easier and it is actually easier and we're coming back in next chapter to describe how to solve this thing and it is rather interesting and simple. Okay, now the electric field need to satisfy two equations but we only need to satisfy one. Okay, this one is trivial and you don't go anywhere, so uh electric field need to satisfy both of it, but potential, you just need to satisfy this one. So this is why we really like to use potential to describe electric field because potential is much easier and it is a scalar function and also only one equation need to be satisfied. So this is why we like potential, electric potential. Okay. The potential of a local charge distribution. So the goal is usually to find electric field. That's the thing we like because we usually know where we put the source is and we would like to know the electric field distributed in space. However, commonly, electric field is rather difficult to obtain, but potential is easier to know in general. So that Poisson equation is something that we would like to solve in general. So when the potential is known, the charge volume charge distribution can be calculated easier. So that's the thing. If we have the total knowledge of potential in space, we will know the uh, charge distribution. So easy. However, though it's given in most cases, that's the thing. Usually we know how the charge is distributed. For example, on a shell or uh, at a point or just on the surface or in a volume, that kind of thing. The charge distribution usually given. So then the potential need to be solved. Then you can get the electric field. So now that's the problem. If we know something here, it is hard to solve this equation because you need something not so easy. Directly calculate the potential to charge distribution is easy, but on the other hand, this is more difficult. So typical problem is knowing source, solving field, solving inhomogeneous differential equation. So this is difficult. So now we back to the point charge. How are we going to deal with it? So here is just the electric field contributed by a point charge. Okay, so that's quite straightforward. And in the cylindrical coordinate, And point charge will be symmetry. So we just put the charge at the center. So there'll be no theta, no phi. So what we lack here is the electric field is at the center. So that is the point charge at the center of the at the coordinate. Okay, now so because we like to know the electric potential, so we use the electric field uh, taking the path integral. So E dot dl, the path integral, will be something like this. So since electric field only along the radial direction or r direction, so we just directly replace dl into dr. That's it. Taking infinite far as potential reference point. So at the very far infinite far apart, so point charge at origin. That's it. So the potential will be from the reference infinite far to the point of interest. This is what we have. And then just remove the vector part. So what we have are all scalar. And just remember we use prun here to refer as the source. Okay, so now here is the potential. So for a point charge, potential is rather simple, almost the same as electric field, but it is scalar, first thing. So there's no R, and also the the denominator is R instead of R squared in electric field. That's it. So the form is rather simple and easy to read. Note 1. Electric field equal to the negative gradients of potential. The negative sign make potential positive for positive charge. That's the idea. Note 2. Choosing infinite as reference point make lower limit 0. Okay, so no big deal. If the point charge is not at the origin, just rewrite the potential. So if the charge is not at origin, so now this is the displacement vector we mentioned earlier again and again. So reference point, your charge, which you plug, and your point of interest using no plug, and the displacement vector is from the source to the point of reference. So the vector funny r equal to the r minus r prime. That's it. So you got whole bunch. So that's the thing. So basically, the potential at r contribute by the r prime source. Just write things down like this because this one is the distance between the source and the point of interest. So it takes the absolute value, just give us the distance or this funny r, and a scalar funny r, actually just the distance. So for multiple charge, just do the same thing again and again from 1, 2, 3, 4, all the way to I. So that's it. This is how things working here. So just superposition it, just add everything together. That's it. For continuous charge distribution, just take the integral. That's the idea. So no big deal. And the prun is reserved for the source. That's the thing. All right. So you got the charge distribution with the charge density at that particular location. So we write things like charge distribution, so charge density as a function of the location in using prun because it's describing the source. That's it. And how much potential contribute to the point of interest is just sum them together. Exactly this form, but using the integration and using prun to represent the source. That's it. So V prime means that the volume has the source and the source distribution, and from the reference point to particular place that has certain charge distribution, and you sum all the volume that charge distributed. So that's this sentence. Okay, now for given Zhou charge distribution, potential can be solved. So here you can take a look at it. Our goal is try to find the potential uh, at any place in the space. So if we know the charge distribution, which earlier we said usually rho is given, so we need to get potential, and then we will solve the electric field. So here we have the charge distribution. So we just do the simple integration of the charge through the charge distributed space. And then we got the potential everywhere in the space. And earlier is still doing this thing, but earlier we have the Coulomb's law, which we have the charge distribution, and we need to do the integration of each charge contribute to the particular place R. And the integration is annoying. Basically, the first thing is the denominator is funny R squared, and also it has a vector. So vector need to be taken care of it carefully because it's pointing certain direction. Vector is annoying. So, but here the potential is easy because it's scalar. So this is a solution for Poisson equation. So we have the potential. So now, as long as we know the charge distribution, we can solve the potential. Given potential, rho can be solved, and that's it. So the original equation, if we know the potential, the charge distribution is easier to be solved anyway. And okay, that's it. So we'll make a short conclusion a little bit later. Anyway, look at it. So the same thing for line charge, surface charge is still the same thing. If it's line charge, taking the path integral, and we got the potential. If it is surface, using the surface charge density, so doing exactly the same thing. Okay, so example 2.a is a uniformly charged spherical shell of radius r. Is still the same thing, and it's exactly the same problem for 2.7, but here is a shell, so we just do the surface integral of your potential. That's it. So just do it. Okay, now that is the basic conclusion of the electrostatic things. So there are three things. The most fundamental is charge. Charge is the source. The source generate field. Okay, so our Coulomb's law telling us the electric field is actually each charge contribute to the particular interested point R in this form. Just each charge distribution or each charge in a tiny volume contribute to the electric field, but in the 1 over r squared manner and having the direction from the charge pointing to the point of reference. Complicated read anyway. So the prime indicate source. So we got prime. And funny R means the point from the charge to the point of reference, point of interest. Okay. So that's the integration form. If you know the charge distribution, you can know the electric field. That's it. And it's annoying because of the denominator and the vector. And also with charge, we know we can obtain the potential. So the potential is scalar, easier. And the form is almost identical with the Coulomb's law, except the denominator is just r, funny r. And there's no vector to deal with. So it's much easier to deal with in compared with the electric field. And then we can have potential. That potential can relate it with the electric field. So potential is in the middle, charge in the electric field, but we can use potential to obtain electric field as well. So here, the relation that between electric field and the electric potential. If you know the potential, you can take the gradients and take a minus sign so the electric field can be obtained. On the other hand, if you know electric field, you just take the path integral and you got potential. That's it. And uh, other way around is the same thing. If I know the if I know the potential, just take the Laplacian, you know the charge distribution. On the other hand, the electric field to uh, char- uh, charge distribution, you know the electric field. You take the divergence, you got something like this. You take the curl, you got zero. So this is almost you can do nothing. Okay, so here are the pretty much all you need to know. So typically, easier things is on the right hand side, and you can do the mathematical operation. You got left hand side easier. That's it. All right. So but this one is your operation is on the left hand side. So you better know the potential and then you can solve it easier because this kind of thing is called forward problem. You know the operation and you got some result. That's easier. So here, pretty much tell us the relation between charge, potential, and electric field. And they can uh, be worked together and depends on what kind of knowledge you have. You know the charge, and then you want to solve potential or you want to solve electric field. You're just using this. If on the opposite side, use the differential form. That's it. That's the idea. And one other thing is not here is just the path integral. If it's a closed loop, it will be zero, but it's essentially coming from this one. So don't worry about that. Boundary condition. Because we try to solve differential equation here, okay, it just if you want to solve the differential equation, boundary conditions are essential. So this is differential equation. So if you want to solve it, we need boundary condition. Slightly earlier in previous chapter, we said to solve differential equation, boundary conditions needed, and two kind of boundary condition is categorized. So one is Newman boundary condition, and one is Dirichlet boundary condition. Each by itself is telling you what to do. Yeah, just the boundary condition is given the value on the boundary, the physical value on the boundary, or the differentiation on the space, what kind of value will be. Okay, so electric field is discontinuous across the surface charge. This is what we want to show you. So here is from the Gauss law, or this is a differential form or the integration form. And integration form is probably easier to work with. Okay, for that, we just like earlier, we say we can choose if this is a surface charge, so surface boundary. So it'll be easier to use something like along the surface. So pillbox is a good boundary we can choose. So we choose a thin pillbox as a Gaussian surface. So the uh, closed surface integral will be the enclosed charge inside this surface. So that's it. So by that, we can take this pillbox as extremely thin pillbox. So we will not worry about the size of the box. Only consider the big area is enough. And since you got the boundary condition, which is the boundary, which is the surface charge, so we can solve the electric field. So the electric field, uh, assuming is more uniform, so the electric field is pointing vertically up, vertically into it. So on both sides is vertical. So only consider this surface area is good enough as long as the box is thin. So here the notation is we use the perpendicular because the electric field pretty much perpendicular to it, and we will say it's above and below. So here the surface the closed surface integral, just like I said, since we consider is an extremely thin box, so we don't consider the side, only consider the top and bottom surface. So the area, since it's a pale box, are the same on both sides, and one is on the top, one is below. So we say above and below and perpendicular to it. So A, the surface vector is pointing up, this surface vector pointing down. So we got things like this. So with that, we have the left hand side. But on the right hand side, how much is the charge enclosed? The enclosed charge is actually the surface charge density times the area of this surface. So it'll be this one. So that's it. So that gives us the first boundary condition is the normal component of electric field uh, is discontinued by amount of surface charge divided by epsilon across the boundary. That's it. All right. The second one is actually the for this curve. So consider we take a loop across to the boundary, and of course again a very thin loop, so just on the top of the surface and below the surface. So now we have a path which going this way on the top and that way on bottom. So what we care about is the parallel electric field. So that we write in down parallel electric field. So now, so this one is equivalent to the closed loop integral, and there'll be 0. So we choose a closed loop across this boundary with uniform surface charge. So uniform surface charge along this distance L. So we only consider the charge distributed here. So we just write things down. Parallel on the top, parallel on the below, and take the integral, and then we get the remove the vector, so it'll be 0. So here is the second boundary condition is the uh, tangential component, or the electric field parallel to the surface will be identical. So the tangential component of electric field is continuous on a boundary. This is the boundary condition we are talking about. All right. So with these two boundary conditions, one is consider the electric field perpendicular to the surface, one is the electric field parallel to the surface. We write things down like this one. So that's it. That's the more general form, vector form of the boundary condition. So consider potential. So we have that. So we take the path integral. So we choose the extremely short line perpendicular across the boundary. So that's by definition. So the potential on top at the bottom is just simply across this boundary. So for infinite short line, the integration is 0. So potential above and below are the same. So potential is continuous across the boundary. All right. So the potential doesn't have to change anything. And also that we got electric field, so we can rewrite it and into the potential above and below, there'll be something like this. So this is direct potential value, and here is actually the normal derivative of the potential. So it gives us the normal derivative of the potential across the boundary, and that gives me another thing to represent. So is the potential above taking the normal derivative minus the normal derivative on the below is equal to the surface charge density, and take a negative sign, epsilon, whatever, like that. So that's it. Okay.